It's the only one that makes sense. As in, it can be recreated. 360 wouldn't be, like if someone designed maths again, and we forgot all math, 360 probably wouldn't be the number.
What do you think it'd be?
It'd probably be something to do with radians. Why is radians? If you think of a circle with a radius of 1, what is its circumference? 2 pi. Yeah, so the distance to go all the way around the circle is 2 pi. And we see that 2 pi is equivalent then to 360 degrees, yeah? Because each bit, the angle as we start here going all the way around, so your angle here is shorter, but if angle go around, it's 360 degrees. So we can say that 360 degrees, as we know it, is 2 pi. And half the way around it is a pi. Yeah? So it's the angles it makes in a circle. And this pi number is very recreatable all the time because it's just any circle in the world's circumference divided by its diameter. And then we can now apply it to the angle in a circle. If you start here, work around, it's the same. So how do we convert between the two? We usually use this relationship. We know that 180 degrees is pi. So if we have 45 degrees, how do we convert it to radians if we have degrees? We want to go to radians. Well, I know that's 45 degrees out of 180. So yeah, well, I think that 180 is a full pi. So I don't have a full pi. I got 45 1/80ths of pi. Yeah?
Mr. Collins?
Yeah.
I'm so confused how you got 360 is the same as 2 pi.
Okay. Circumference. What's the circumference of this circle? Yeah, the circumference is yeah, okay. Yeah, 2 pi r. Yeah, sorry. I jumped that pretty fast. So the circumference is directly related then to the angle that goes around it, yeah? Okay, so that's the formula you could use if you want. You can multiply whatever angle you have. So the angle multiplied by pi over 180 will convert it for you. And the opposite operation then if you want to go the other way.
Is that what we do with? Never mind.
So if you have 60 degrees, we can convert that pretty quickly by multiplying by pi over 180. Do a quick cancellation, that's 1/3. Okay, so it's pi over 3. Yeah? Okay, so that's radians. You're going to see. Because 180 degrees is exactly pi. So you're getting what fraction of 180 you have.
So you get the same answer in 2 pi.
Yeah, and 2 pi is 360 though, but for conversions it's easy to just stick with 1 pi. It's like converting between degrees and Fahrenheit, you would go with 1 degree rather than what 2 degrees is. Yeah.
Would this only work if, would it really make sense? Because pi over 3 wouldn't be like a circle with radius of 200.
Pi over 3 is 1/3 the distance around the circumference.
Oh.
So it's 1/3 of the pi distance. So it'll be about this much. So remember, pi distance is this far. So it's 1/3 of that. Oh, that's about 60 degrees. And 2/3 of it around this much. So that's 120. So the common ones you see all the time are 60 degrees, which is pi over 3. 45 degrees, which is pi over 4. 30 degrees, which is pi over 6. And 90 degrees you see a lot, which is pi over 2. They're very common. You have to switch between those all the time. Okay. So I'm going to try and use these as much as possible without saying these anymore, and you're just going to have to remember. These are the ones that are common. Otherwise, you'll have to just, and of course, 180 continues that trend to pi. Okay, so that's converting between radians and degrees. Now we're going to look at sine, cos, tan, and then the unit circle. Like sine, cos, tan work off a right angle triangle, don't they? They're the ratios of the sides. So if I have theta here, Sine is the ratio of the opposite side to the hypotenuse, isn't it? Yeah. So sine of theta is the opposite over the hypotenuse. And maybe you could see that if the opposite side got shorter, the angle would be smaller here. Yeah, and if the opposite side got bigger, the angle would be bigger, so much so that if the opposite side was almost the same size as the hypotenuse, it would almost be 90 degrees as well. Of course, that couldn't happen. If the opposite side got as large as the hypotenuse, they'd have to kind of almost meet in a straight line. The triangle would start looking like this. Really long triangle. If these were almost the same length, it'd be 90 degrees, yeah? So it's going towards, sine is, as the opposite side gets bigger, the angle's getting bigger. Okay? Now, if we were looking at cosine of the exact same triangle, this adjacent side, cosine, the adjacent over the hypotenuse, which you've done before. As this one gets bigger, what happens to the angle?
It's smaller.
Yeah, it gets smaller. So you can see here, a really small adjacent side in this weird triangle has a really large angle. Yeah? So it's the exact opposite relation with sine. They're exact opposites, yeah. So as the opposite side, as sine gets bigger of an angle, the cosine gets smaller. So these are a ratio. It uses off the hypotenuse, and tan also has a ratio, opposite over adjacent. This is the only one allowed to be greater than 1, isn't it? Why? All of these have to be less than 1. Anybody tell me why these have to be less, or yeah?
90 degrees is comparable to 1 in I don't know.
Okay, yeah. Ryan? Yeah. Hypotenuse is must be the longest side for a right angle triangle to work because it's opposite the biggest angle. Like triangles work like that. The angle opposite the biggest side will be the biggest angle. So these two cannot be more than 90, otherwise they wouldn't be the biggest side. Okay. So, but tan, we can form a right angle triangle that has a really large opposite and a really small adjacent. And that's still a right angle triangle. That's okay. The ratio of this would be 3/1. That's okay. But this side would still be the biggest one. Okay, so that was from our GCSE maths. You would have done that a load of times. And then you may have come across the unit circle. You should have. Briefly, yeah, maybe.
Never answered that questions on it.
No? Okay. Right, the unit circle is based off a circle. Where's the unit come from? What's the unit bit mean? Kinda, yeah. 1, so unit usually means 1. What's 1 in this circle? The radius is 1, yeah. The radius is 1. It's back to that circle I was doing. The radius is 1. So we got 1 all directions. So the circle is always 1 unit away from the origin. So like the coordinate here would be 1, 0. Coordinate here would be 0, 1, minus 1, 0, and 0, minus 1. Yeah, happy with that? Yeah. Okay. We've been dealing with angles already in the circle. As we start off here with the real axis, and as we move around, we create angles. And remember, the full thing was 2 pi, if you remember that, which was 360 degrees. Let's create an angle here in this first quadrant. Draw a right angle triangle. If I can have a blue marker, it'd be nice. Yeah, I do. So I'm going to just create some angle here. Let's call it our classic theta. There's a right angle triangle there. I've created this angle with the x-axis, and I've created a right angle triangle. Now, one thing I do know about the hypotenuse of this right angle is it's 1, yeah. That is useful. Now, I'm going to use these ratios. So what is this x length here? Well, using my ratios, the only thing I could say about it is that cosine theta, why do you use cosine? Because I have the adjacent and the hypotenuse.
Wouldn't it both be x? Wouldn't the opposite be x too?
This? No, I'm just calling it x, but I'm using x because it's along the x-axis, and I'm going to call this one y because it's along the y-axis.
He's saying, are they both?
If it's 45 degrees, it'd be the same. It kind of looks like a 45 degree one, but I can't presume that. Yeah. So cosine of theta will be the adjacent side, which is this side, x, over the hypotenuse, which is 1. Now, a division of 1 doesn't really do anything, does it? So it's just cosine theta is x. So that length from here to here is cosine theta, yeah? Because x is cosine theta, we just did that. Which means this coordinate up here is also cosine theta, because when we give a coordinate, you give the x value, but we know whatever cosine of the angle is, it'll be a decimal. I know the decimal between 0 and 1, because it has to be, because we know that, but also even on this circle, you can see it's going to be between 0 and 1, because that's as far as 1 goes. Sine theta follows something identical. Sine is the opposite, y, over 1. So y is sine theta. So instead of putting y here, I know that that height would be the sine of the angle, the decimal value for sine. Which means along the y-axis, this is. As I go around, or maybe you can just stick to this first quadrant if you want. Anytime I draw that triangle, whatever the angle is, the coordinate up here will be cos of the angle, sine of the angle. No matter where I draw it. Does that make sense? Because of the fact that the hypotenuse is always going to be 1, no matter what triangle I draw. So that means in general, I can say that the x-axis is directly related to the cosine of the angle made here. If I make the angle off the x-axis, yeah? And that the y-axis is directly related to the sine of the angle. Because I'll just do this over and over again, and wherever I draw it, it'll sine and cosine. Now, we have a few things that we already knew. We wrote down 4 points at the very start of this whole thing. We wrote down this, we wrote down that, and that. Coordinates, we knew them. So what does this refer to when we talk about an actual angle? What's the angle before we start? We're still flat here. What's that angle? 0, yes. So I can say from this that the cosine of 0 is 1, yeah? And the sine of 0 is 0. Because every point, the x value will be the cos of the angle, and the y value will be the sine of the angle, no matter what the angle is. And therefore, at this point then, the cosine of a 90-degree angle, which is what this would be all the way up here, yeah, is 0. And the sine of a 90-degree angle is 1, because 0, 1. Yes? Now, and we can continue this process. This moves around, and if we just think about it's the angle the radius makes with the x-axis starting point. Because once we're talking about circles now. Once we go on past here, the kind of notion of a triangle with more than 90 degrees, or definitely when it gets to more than 180 degrees, if we kept going, doesn't really make any sense. So now we're talking about circular motion instead of just in triangles. As the angle of a circle gets bigger, what's its sine, cos, and tan? So when we get to this point, the angle has gone all the way around to here. That's watch the radius spinning around. That's 180 degrees. So the cos of 180 degrees must be the x value here, -1. And the sine of 180 degrees is 0 again. Yeah? Because we knew that point. That point is definite. And if we continue this process, we get to 270 degrees. So the cos of 270 is 0. And the sine of 270 is -1. Now, of course, we probably should be using radians at this stage, but we'll stick with degrees just because you're more used to them. So that would be pi over 2, pi 3 pi over 2. And 2 pi, we go back to this. So I know that the cos of 360 and the sine of 360 is 1 and 0 again. And of course, circular motion keeps going. You can get this, therefore you get the sine and cos of any angle. Couldn't you? You just keep going, you just find out what spot it is on this circle, and you get the sine and the cosine of it. Because you would have done in GCSE that what shape that makes, as the angle keeps getting bigger, the function oscillates, doesn't it? It doesn't shoot off anywhere, it just keeps coming back to the same numbers, yeah? And that's this thing. Just keeps coming back to the same numbers. It oscillates between 1 and minus 1. For this reason. The angle would just, the angles get bigger, the angle's getting bigger, yeah. But the value it creates, the ratios, just go between 1 and minus 1. Okay. Now there's a bunch of special triangles. 2 special triangles that it's good to know the angles off by heart from. Good to be able to recreate, and they come up constantly in paper 1, which means you need to know them, and they're not in the formula booklet. These are the known triangles. The most obvious one is what happens if it's 45 degrees. So if we have a perfect isosceles triangle, this is 45 degrees, this is 45 degrees. Let's say they're both 1 distance. We create this triangle. That's a right angle isosceles triangle, isn't it? What's this other side? Square root of 2. Yeah, 1 squared, square rooted. Okay, so the sine of 45 degrees is 1 over root 2, yes? And the cosine of 45 degrees is also 1 over root 2. And that would be, if we drew it in here, it'd be about here, 45 degrees. Okay? What's the sine of 135 degrees? I want to know the sine now of 135 degrees. I want a Cert value. Yeah, it's also 1 over root 2. Why?
Because it's just on the perfectly other side of
It's a perfect reflection. If this, let's say this is 45 degrees, then I know that this, the cosine of it is 1 over root 2 from here. And the sine of it is 1 over root 2. That's the point, 1 over root 2, 1 over root 2. If I had 135 degrees, that would go around to here. Where's the link with 45 degrees? This angle's 45, isn't it? The angle here is 135, but I'm knowing 45 short of 180. Yeah? So you could think about it like this right angle triangle, if you want. Now my diagram's not great, but this is should be exactly in the same position as that. The y value should be exactly the same. 1 over root 2 for sine. What's the cosine of that? Yeah. So the sine of 135 degrees is the same, but the cosine of 135 degrees is negative. And it's negative, you can see this negative because the cosine is directly related to the x-axis, and there's no way that could be a positive value. Yeah.
Why don't we start there? Like, why don't we start on a different axis?
Why do we start here?
No, like on the other side. Why don't we start on the right side?
The reason is actually got to do with complex numbers, but we won't get there yet. But yeah, this is just, take it for now that we always start with the positive x-axis. And in complex number, that will be the real axis. But yeah, and then we go this way because it doesn't really, it's anti-clockwise, it doesn't make sense, but it is the way we normally measure angles because of complex numbers. Again, the multiplication of complex numbers goes that way.
Country or, I don't
No.
know.
It makes sense why we go this way, and when we do it in complex numbers, it's about multiplication of complex numbers. They go that way for some reason. Maybe the thing that doesn't make sense is the clock goes this way. Okay, all right. So there's a bunch of these that you might have, you can see that we have the unit circle over here. You see this thing that's created. There's another known triangle. The 1, 1, 45, 45 is one of them. What's the other one? What's it created from, the other one? What do I start with? I start with a triangle. It's not actually a right angle triangle. It's a different type. It's an, no. What's the other one? What's a perfect triangle? Yes. So you start with that. That's 60 degrees. That's 60 degrees. These lengths, let's call them all 2. I split it in half, yeah. So if I split it perfectly in half, perpendicular bisector, then that's going to be 1 and that's going to be 1, yeah? And I don't really care about this side anymore. I just know that that's 30 degrees, because 30 and 60 and 90. What's this side? It'd be this squared, take away this squared, which is 4, take away 1, just root 3. And then you could create your angles off this. The sine of 60 degrees will be the opposite over the hypotenuse. The cosine of 60 degrees is the adjacent over the hypotenuse. And the tan of 60 degrees can be created by this over this, root 3. Or you could have done it from this, over 1 if you like. And then the sine of 30 degrees, we start to realize the symmetry of these two, it happens to be a half, which is the exact opposite to 60 degrees. And the cosine of 30 degrees is root 3 over 2. Now you can do that. You'll be looking from the 30 degrees. This is the adjacent side. This is the hypotenuse, so root 3 over 2. And then the tan of 30 degrees is 1 over root 3. So you have to know these off by heart. So how do you remember them? Some people do the hand. I have a different way, of course. I do sine, cos, tan. I remember that. That's pretty easy. I remember my angles increase from 30 degrees, which is pi over 6, 45, 60, so pi over 4, pi over 3, and pi over 2. I do 1, 2, 3, 3, 2, 1. 1, 2, 3, 3, 2, 1. And then I know that they're all over 2. But, as you can see, the root, this is square root, and this is also square root. So they're all square roots. The 1 is even square. This is how I remember it. So 1, 2, 3, 3, 2, 1. And then tan is this one over this one. 1 over root 3. Root 2 over 2, which is just 1. Root 3 over 1, which is root 3. And this is increasing. This is getting bigger. So it's going towards 1. This is getting smaller towards 0.
Oh, for tan, it's just tan.
You can think about it that way.
So then tan pi over 2 would be 3.
Oh yeah, what's this one then? Tan of pi over 2. 3.
Wait, can I draw that bit?
Oh, no.
Yeah. So sine over cosine is tan. So tan of pi over 2, or 90 degrees, is 1 divided by 0, which is what? Why is it undefined? Why can't you divide by 0? It's not allowed. All right, if you're allowed to divide by 0, let's take a different example. Let's say we say 6 divided by 0 is 0. Let's say we say that, right? Yeah. Well, something we know about multiplication and division is they work in absolute opposition. That 3 times 2 is 6. Therefore, 3 is equal to 6 divided by 2. Yes? If that follows, then this would mean that this is true as well. The opposite would have to be true, working the other way, working backwards. And I'm pretty sure that 0 times 0 does not equal 6. So there's no product that will give 0 times 0 will never produce 6. So that's illegal and is undefined, not 0. So you'll see an undefined or an error if you put it into your calculator.
If you think about it like what's called indexes, wouldn't 6 divided by 0 be 1?
Why?
So if you do like 2 to the power of 0, it'll always be 1. Or if you do 6 to the power of 0.
Ah, okay. Well, why is 2 to the power of 0 1?
It's just 2, I understand that.
No, 2 to the power of 0 is 1.
Why is 2 to the power of 0 1? Why is anything to the power of 0 1?
Because 2 to the power of 1 is 2, 2 to the power of 2 is 4, and so there's a pattern.
Yeah, yes, it's completing the pattern, yeah. So 2 to the power of 4 is 16. 2 to the power of 3 is 8. So that's something we know.
Anything to the power of 0, 1?
Yes.
Yeah, but we also know 2 to the power of minus 4 is 1 over 16. Yeah? And 2 to the power of minus 3 is 1 over 8. And 2 to the power of minus 2 is a quarter. And 2 to the power of minus 1 is a half. Now what's happening when we're going this way, what's happening? We're dividing by 2. I've left out a couple. 2 to the power of 2 is 4, so that's also dividing by 2. A half divided by 2 is a quarter, yeah? And so these are all, so there's something, we got to keep this going. So that's 2 to the 1 equals 2, so that's also dividing by 2. Now how do we bridge this gap? Because the pattern is 4, 3, 2, 1, 0, minus 1, 2. So this must be 1 to fill in this pattern of dividing by 2s, like the balance point, if you want, between negative powers and positive powers. Yeah. That's one explanation. That's the only one I'm doing now. All right, that was not required, but it maybe answers your question.
Yeah, no,
Okay. Therefore, quite often with the unit circle, now I am running through this because it should be revision, and maybe it is not. Maybe it is the first time you're doing something. Okay. That we can say something about angles when they hit a certain quadrant. We can know that in the first quadrant here, all ratios are positive. What do I mean? All these numbers are going to be positive. So the sine of all angles between 0 and 90, positive. Cosine of all angles, positive. Because you'll get coordinates that are just positive x, positive y. There's no way we can get a coordinate in this quadrant that's negative, can we? No, it's impossible to get a coordinate that's negative. When we move into this quadrant, I know that all cosine coordinates are going to be negative, yeah? Because they're all going to have a coordinate here on this axis. So its x coordinate is always going to be negative. You're going to be basing it off this axis, yeah? But all sine is going to be positive, yeah? Because they're still positive. So some people put an S here for sine is positive. What's tan going to be in this quadrant? Negative, because a positive divided by a negative, sine divided by cosine. What's going to be positive here? Well, both sine and cosine are negative, so that means tan is positive. And the last one over here, a point here, the cos would be positive and the sine would be negative. Yes, you might remember that. No, okay.
Do we need to remember that?
Yeah. Yeah. You'll logic it out pretty quickly because you'll always be thinking of the x-axis as the cosine and the y-axis as the sine. And if you find sine 220 degrees.
When was the sine y-axis?
It came from this thing at the start when I did the opposite of the angle is always over here if the angle is made with the x-axis. Okay. One more thing on the unit circle before we move on to points of space. You probably need to practice this a bit. Is the Pythagorean identity, which is taking this right angle triangle, which we know to be 1 sine theta cosine theta in length. Pythagoras states that cosine squared theta, this squared, plus sine squared theta, this squared, is equal to 1 squared.
Wait,
And one.
Is that squared cosine times theta?
Yeah, so you may not see that this cosine and sine like this is the same as this. That's the same. That's the same. It's the same terminology, it's just written differently. Means the same thing. So cosine squared, that length squared, plus that length squared equals 1 squared, which is just 1. So this is the Pythagorean identity, which is useful. If you know the sine of an angle, you can find automatically the cosine of an angle straight away. How? Using this.
Sine squared minus 1 cosine.
The Pythagorean, it's in your formula booklet. You won't need to remember it, but it's,
Why don't they talk to you about that in IGCSE? Because that's not that long, and it's like, that would help us.
wouldn't really, the questions wouldn't really, it is in your GCSE course, but maybe you don't remember. So, if I know that sine theta is 3/4, now that's not a known angle. It's not here. 3/4 is not written here. Can I find what the cosine of the angle is? Yes, straight away. Because I know that cosine squared plus sine squared theta is 1. So if I square this, I get 9 over 16 is equal to 1. Bring that over here, subtract it over. I get cosine squared is equal to, is it 7 over 16 if I subtract? And then the cos is the square root of that, which is root 7 over 4. So I know that the cosine length is root 7. The hypotenuse length is 4. I knew that anyway. And the opposite length is 3. They're in that ratio, yeah.
How is cosine squared 7?
Because cosine squared plus sine squared will always equal 1. Always equal 1. For this, okay. All right. Yeah, so that was a lot.
Wait, and then with those two, you can draw the triangle, right? Once you have the coordinates.
The other way of doing this is you can just draw a scaled triangle. So you can have a guess. So this length is 3, this length is 4. What's this length? If that's theta, what's this length? It's going to be 4 squared minus 3 squared, which is root 7. You get the same thing. This is, of course, the ratios of these sides. We don't know if that's the actual length, if that was the question, if that's the actual length of the sides, but that's the ratio the sides are in. Yeah.
Is it just on the question, but since it's a 4, and it's like over 4, could theta be like 1 over 4, and then 1 over 4 of 180 would be 45 degrees of the example?
Okay, so think about the ratio. Remember, you've created a ratio, not the angle. So you said that, was it sine or cosine theta was 1/4? All right. You're saying sine of some angle is 1/4. Is that angle then 45 degrees because it's 1/4 of 180? If you just drew this triangle, remember this is a decimal representation of the opposite side divided by the hypotenuse. So an opposite side of 1 divided by a opposite side of 1 divided by a hypotenuse of 4, that's 1, that's 4. That's looking like it's not going to be a very large angle for a start. So what is sine of pi, which is what you're saying? All right, sine pi over 4.
Yeah, what does the 4 represent then?
Here,
No,
it's 1/4 of 180.
In sine theta, 3 over 4. So you're saying sine theta is equals 3.
Sine theta is the ratio. Sine and cosine and tan are ratios. They take two sides of a triangle and say, all right, one is bigger than the other by this much. Therefore, the angle must be this. It is not the angle. Remember, when you did GCSE, you said theta was sine inverse 3/4 to get what it was, what the angle was.
Oh, so now in the cosine thing at the bottom, you're saying that cosine is equal to square root 7, but then
Yeah,
hypotenuse is 4.
yeah, of the same. So 4, 3, root 7, and 4 have that
That makes a lot
relationship.
of sense.
Okay.
Why would you ever use the Pythagorean identity when you can just do 4 squared minus 3 squared?
Yeah, you can do either. Yeah. This is quite a simple identity, which can be easily done just drawing a triangle.